In our next two examples, we're going to look at some special situations that sometimes come up when you're trying to solve a system using substitution or elimination. Suppose we look at this system that we have here, and since the x in the first equation is almost by itself already, suppose we decide we're going to solve this system by substitution, getting x by itself in the first equation and substituting for x in the second equation. To get x in the first equation by itself, we would add 3y to both sides, leaving us with x equals 3y minus 2. When we substitute for x in the second equation, we would have negative 3 times a parentheses plus 9y equals 5. And in that parentheses, we would put 3y minus 2. After we substitute, we distribute. Negative 3 times 3y is minus 9y. Negative 3 times negative 2 is 6. So we have negative 9y plus 6 plus 9y equals 5. After we distribute, we combine like terms. And notice here, our like terms, negative 9y plus 9y, those are opposites, and they cancel each other out, leaving us with 6 equals 5. This is what we call in algebra a number sentence, when there are no variables on either side of the statement. And in this case, 6 equals 5, well, that's not true. 6 is not equal to 5. We have a false number sentence. If you're solving a system of equations and you have a number sentence as a result, the first thing you should do is go back and double check your steps and make sure you've worked through the algebra correctly. If you've worked through the algebra correctly and you have a number sentence that is false, such as 6 equals 5, that means that your solution to the system doesn't exist. We can say there's no solution to this system of equations. A vocabulary word we use to describe the system then would be to say that this would be an inconsistent system. Let's take a look at another situation that sometimes comes up in our next example. Here we have 2x plus 5y equals 1, negative 4x minus 10y equals negative 2. And suppose we decide that we're going to solve this using the elimination method by focusing on the x's. We have 2x on the top equation, negative 4x on the bottom equation. We could get opposites for the x's by multiplying everything in our top equation by 2. When we multiply that by 2, we would have 4x plus 10y equals 2. And when we add these equations together, the x's are opposites, so they cancel out. The y's are also opposites, so they would cancel out, and all we would have on the left side of the equation is 0. On the right side, negative 2 plus 2, those are also opposites and cancel out, so we get 0. Here we have another number sentence. The difference between this example and the previous example is that here our number sentence is true. 0 is equal to 0. This system is the sort of system we looked at when we were graphing, where you graph the first line and then the second line turns out to be another copy of the first line right on top of it. Here we would say there is an infinite number of solutions, or you can say infinitely many solutions. There would be infinitely many points that would make both equations true. And a vocabulary word we use to describe that would be to say that this is a dependent system of equations. One thing that's very important on this type of problem, putting all real numbers would be an incorrect thing to do. our solutions aren't numbers. Our solutions are points. So you can't say all real numbers for this problem. It would be more correct to say infinite number of solutions.